This is a little video to demonstrate the localization and de-reverberation processing developed during the EARS project. To wrap everything up, we have this little graphical user interface which allows us either to record live audio from a 12 microphone robot or from a 32 channel spherical microphone array. Today we're going to use a pre-recorded signal which was recorded at the EARS review meeting in April 2016. This is a photograph of that occasion, and you can see the spherical microphone array over here. The original audio sounds like this.
This is another demonstration now using a third order.
So in that recording you can hear my voice probably as the most dominant, but there are also additional speakers and a large amount of background diffuse noise from many babble speakers. So I've started the processing going, and the first algorithm to run is the subspace pseudo-intensity vector localization algorithm. This operates in the spherical harmonic domain and builds on some of the ideas developed by Boaz Rafali at BGU in Israel. So it uses frequency smoothing to decorrelate the reflections and a subspace decomposition of the spatial covariance matrix. But where we differ is that we use the primary singular vector directly rather than computing a music spectrum over the noise subspace. By using this primary vector, we can apply our pseudo-intensity vector method directly, which means that for each time frequency bin we get a single direction of arrival. These directions of arrival are together formed into a histogram, which you can see on the screen. So here we can see that there is one source here, a small amount of a source here, and then this one here is just a spurious peak. So we have identified with the circles the directions of arrival that we want to be able to listen to. The next stage in the processing is de-reverberation, which is using a long-term linear prediction-based method which we have implemented in the spherical harmonic domain. This aims to remove the long-term reverberation whilst leaving the interchannel relationship between for the early reflections intact, which means that we can then apply some beamforming pointing in each of the directions of the identified sources. Finally, we apply some conventional noise reduction using a minimum mean squared error approach. Each of the enhanced signals is then sent to a cloud-based automatic speech recognition server to give us a text transcription which appears in this box here. In this case, we are currently seeing the transcription of the unprocessed audio. When I play the processed audio here, it will start off with actually the unprocessed, and as I press the mouse on each of the identified sources, you will both hear the speech and see the transcription.
This is another demonstration now using a third order. This is another demonstration now using a third order.
So there you could hear the original signal and the ASR managed to pick up only the first three words.
This is another demonstration now using a third order. This is another demonstration now using a third order.
I am flying home tomorrow. I hope that my seat on the plane is comfortable, otherwise I won't be able to get. I am flying home tomorrow. I hope that my seat on the plane is comfortable, otherwise I won't be able to get.
This is another demonstration now using a third order. This is another demonstration now using a third order. This is another demonstration now using a third order. This is another demonstration now using a third order.
So you could hear that the two dominant speakers were significantly enhanced, and the transcription became, in the first case, almost perfect. In the second case, we do identify the start of the utterance, but not the end. And for the third speaker, which is of a much lower level, the transcription was incorrect, but the beamforming and dereverberation processing still helps to pick out that source. And then, as stated previously, the fourth source is actually not a real source at all. Thank you.